fiber optics deliver images and sound to your phone. Fiber optic cables are made up of thousands of bundles of optical fibers, each as thin as a hair. The optical signal carries a lot of image and sound information through these tiny channels. So how does it work? Let's look at an interesting experiment. This is an ordinary fiber optic cable. Let's take a small flashlight and shine it through one end of the cable, and the light will come out from the other end. Isn't that amazing? Is the light bending inside the fiber optic cable? Why else would it come out the other end? Actually, the light is still traveling in a straight line. It's not really bending. Let's go through the following experiment. You'll understand once you see it. So this is how optical fibers work. Elementary school knowledge tells us that light travels about 300,000 kilometers per second in a vacuum. If it passes through a different medium, the speed will change. This change in speed is expressed in terms of refractive index, which also leads to another interesting phenomenon. For example, when light passes through this transparent prism, we can clearly see that the light bends as it passes through the interface instead of staying straight. This phenomenon is called refraction. The reason for this phenomenon is that air and the prism do not have the same refractive index. When light passes from a medium with a high refractive index into a medium with a low refractive index, it bends. Like this pencil, when it passes through 3 different refractive indexes, air, glass, and water, it looks like it is bending. It is this seemingly simple and common refraction phenomenon that is effectively used in optical fibers. Now let's say that the prism changes its refractive index by doping it with another medium. As the refractive index changes, the light will slowly move closer to the surface of the prism. When the refractive index reaches a critical point, the light suddenly returns to the first medium in the form of pure reflection. This phenomenon is called total internal reflection. If we change the angle of incidence of light without changing the refractive index, total internal reflection will also occur, and this angle is called the critical angle. Scientists use this phenomenon of total internal reflection of light to trap light in a medium interface and transmit information at the speed of light. The simplest form is fiber optic cable. It's a micron-sized round tube of glass made from ultra-pure silicon dioxide. It has a very high refractive index. When a laser beam hits the mirror at an angle greater than the critical angle, total internal reflection occurs. This means that the light travels all the way to the other end in total internal reflection. From the outside, it looks like the light is bending along the fiber optic cable tube, but the light isn't actually bending, because every time it's refracted, it's moving forward in a straight line. Remember the point. Total internal reflection occurs at the interface between a medium with a high refractive index and a medium with a low refractive index. For example, total internal reflection now occurs between a fiber optic glass tube with a high refractive index and air with a low refractive index. But there's a problem here. The fiber optic glass tube can't be exposed. The protective coating will take the place of the air. At this point, there's no interface between high and low refractive indices, and total internal reflection will disappear. So what should we do? The total internal reflection caused by the housing will disappear. That's easy to solve. On top of the fiber core glass, another layer of low refractive index glass is wrapped around the outside. With the interface conditions of high and low refractive index, the total internal reflection phenomenon resumes. At this point, the outermost shell will no longer be affected. Of course, it is not yet possible to create a material that can reflect 100% of the light source. So the light is slowly lost over long distances in total internal reflection, decaying as the distance increases. That's why you need an amplifier at some distance. It's used to increase the strength of the signal for longer distances. Back to the previous topic, how does optical fiber transmit information? It's complicated to explain in detail. I'll explain the basic principle. Imagine you send a picture to your friend in INS that you just took. The picture is not physically sent, but the phone converts the picture into a digital form. For example, it's a string of zeros and ones, and then the digital code is sent over the internet in binary form. All sound, pictures, and video can be represented in this way. The cell phone on the receiving end decodes the code. The cell phone then acts as a super easel and redraws an identical picture for you based on the digital information sent to it. Of course, the process of fiber optic transmission is more complicated than this example,